afternoon, everyone. This talk is gonna test and evaluate the ISS internal multiple attenuation algorithm given the word to be inelastic. So the inverse scattering series communicate that you can achieve various seismic data processing objective directly and without any subsurface information. And by the theory from Professor Weglein, we know that for both the surface multiple and internal multiple, those subseries not only don't care about the subsurface information, they do not care what kind of model type you have. You can change your Earth model to be acoustic, elastic, or inelastic. For both surface multiple elimination algorithm and internal multiple attenuation algorithm, those algorithms will always remain unchanged. Okay, next, let's briefly remind ourselves the performance of the ISS internal multiple attenuation algorithm given different Earth model type. First, if the Earth is a heterogeneous acoustic, then by using the homogeneous acoustic as the background, Rudel and Weglein demonstrate that this ISS attenuation algorithm can predict the internal multiple with the exact time and approximate amplitude. Second, if the world is heterogeneous elastic, then per the work done by Coates and Weglein in 1996, they found that by using a homogeneous acoustic as the background, this attenuation algorithm can even predict the converted internal multiple effectively, say a wrong model but a satisfying output. Now, if the world is heterogeneous inelastic, where the propagating wave field will be attenuated and the velocity will be dispersive, I'm going to show you how this attenuation algorithm performs by using a homogeneous acoustic as its background. No absorption, no dispersion. Well, the interest of this study is from the reality that you are often part of the world that absorption and dispersion matter. For example, you can, in the pre-salt place in deepwater Mexico or in Red Sea, North Sea, in those areas, you could suffer a lot from the absorption and dispersion. And under these circumstances, you like to have some confidence that even in a world with the absorption and the dispersion, you don't have to specify those properties. This attenuation algorithm will remain its effectiveness to give you the exact time and approximate amplitude prediction. Okay, next we're going to analytically and numerically examine this attenuation for data with Q absorption. Let's look at the analytical part first. In this session, we're going to give you the model. Then you can analytically express both the primary event and the multiple event. Substituting this analytical event to this attenuation algorithm, your prediction result will be analytical as well. So now you can analytically compare your predicted internal multiple and the actual internal multiple, see what happens. But keep in mind that here we give the model to create this synthetic data, but this ISS attenuation algorithm does not take any information about them. Okay, the ISS attenuation algorithm is designed for both 1D Earth and multi-D Earth. Here for simplicity, we just use a 1D normal isness to show you how it performs. Now the model we're going to use is a two-reflector model. You do not have the free surface, therefore there is no surface multiple, no ghost. And both source and receivers are located at the depth of 0. Now for each layer, basically we have 3 layers here. We will have the velocity C, the density rho, and the quality factor Q. So now you can see all these C here is actually frequency dependent. So it has already incorporated both the absorption and the dispersion effect. Now with this model, we're going to generate the 2 primary events and 1 first order internal multiple in your data set. Now this chain actually shows you how to implement the ISS attenuation algorithm. First of all, we want to transfer the data from time domain to the frequency domain. So in this domain, you're gonna able to analytically express both primary and internal multiple, and these two formulas shows you the expression of the primary. As you can see, all these velocity terms here are frequency dependent, so all these, both of these events suffers from absorption and dispersion. Next step, we're gonna map the data from frequency domain to the vertical wave number domain. Please notice that when we do this mapping from omega to kz, we use a constant velocity c0 here. So even the word is with absorption and dispersion, but this ISS attenuation algorithm just use a constant velocity to do the mapping. That's the key here. Next, we're gonna use the stall migration to map the data from the vertical wave number domain to the pseudo depth domain. Since we use a constant velocity c0 to do the migration, so the absolute depth of different events is not accurate. But the relative depth relationship among different events will remain the same as the actual. That's the most important information here. Next, with the data in the pseudo-depth domain, we're going to apply the ISS attenuation algorithm. This is the integral algorithm, as you saw earlier from Yanglai's slides. We know that we have three integral terms here, and 3b1 here actually represent these three events here. And notice here the integral limit, the up limit for z2, I mean z1 minus epsilon for z2, and the lower limit z2 plus epsilon for z3 will ensure that this algorithm can automatically select the events that satisfy deeper, shallower, and deeper relationship. So go through a set of calculation. We're gonna have the prediction result B3 with its analytical form. Now, if we compare this analytical B3 with the actual internal multiple IM, we're gonna have this relationship formula here. This is the prediction, this is the actual internal multiple. You can see there are actually two terms connecting these two atoms here. The blue term here, we call this TF, the transmission factor. It accounts for the transmission loss at the interface is at and above the interface where the multiple has its downward reflection. So for this model, we know the multiple is downward reflected at the first interface. So only the first interface is involved in this factor. Okay. The second term is the red term, QF. We call it the Q absorption factor. It accounts for the energy absorption or the transmission loss in the layers above the interface where the multiple has its downward reflection. So for this example, we know only the first layer will involve in this factor. Now you can see with these two terms, there is actually a global transmission loss starting from the top and down to the place where the multiple is downward reflected is estimated to make the prediction amplitude to be approximate to the actual or smaller than the actual, but the time is exact. This is the key message. So now for simplicity, we just use a 1D normal instance with two reflectors to show you what happens here. But this property will remain the same. We'll have either 1D with multi-layers or multi-D. Okay, again, let me remind you what happens here. We put the data through absorptive and dispersive medium, but this ISS attenuation algorithm does not have that in its reference medium because its reference is selected to be a homogeneous acoustic. Given all that, you can predict the internal multiple with the exact time and the approximate information. This is the key message we are investing here and like to deliver in this talk. Next, I'm going to use a specific example to examine this method for data with Q absorption. This is the model we use here to create the pre-stack data. The work is done during my intern at Schlumberger 3 years ago. And we have 5 layers here with 4 reflectors. And each layer comes with Q absorption. So we use this model to create the synthetic data, but the algorithm itself does not take any information about either Q or density velocity except the data itself. So with this model, we have this input data. Now you have 4 primary events as indicated by the red arrows here, and all the other events are actually the internal multiples indicated by the blue arrows. There's no free surface, so no surface multiple here. Now this is our input data. This is the prediction result. You can see this is the input, this is the output. So you can see only the multiple event is predicted in the output. If we do the comparison, you can see the time is exact and the amplitude is smaller than the actual. Again, this is input, this is output. And besides that, this prediction never touched the primary energy. If you focus on this event, the first primary event, you can see it interfered with the multiple at some offset. But this algorithm only predicts the internal multiple without damaging the primary event. You can pick 2 trees to see more detail here. One at offset 0 meters and the other at offset of 1250 meters. So all these, both of these blue line represent your input data, and these green arrows point to your internal multiple of your input data. This is our input. This blue line here represent the predicted internal multiple. Look at all these internal multiple events, you will see the time are always accurate and the amplitude is smaller. And in the middle of these internal multiples, you may have this blue curve here. This is actually the false primary. You can see this algorithm never touched this primary energy, but just focus on working to predict the internal multiple. So now we have shown you the analytical example and the numerical example. We both come with the same conclusion, exact time and approximate amplitude. This work is adding to the theory that the ISS attenuation algorithm is model type independent. And if you are in a world where the absorption and the dispersion matter, you're going to have confidence that the time will be exact and the amplitude will be approximate. So now we know that the ISS attenuation algorithm can finish what we expect. If you are in the situation that the multiple is not interfered with the primary, then it's enough for you to have the ISS attenuation algorithm plus adaptive subtraction to achieve the internal multiple removal. But if you have the situation that the multiple is interfere or proximal to the primary event, from Yanglei's presentation, we know that the elimination algorithm is preferable in an inelastic medium. Next, my colleague Chang Fu is going to show you his advance to the ISS elimination algorithm with the Q absorption.